Thank you, Armando and INDICASAT team, for a very generous introduction and a very warm welcome. I'm delighted to be here. Panama is wonderful, people are lovely, and indeed it is hopefully going to open up more visits and more collaborations in future. As Armando introduced me, I'm not going to say more about me, it's just Geetha. I'm coming from Belfast, but originated indeed from India. That's the pathway of chemistry career that I took. So, I'm going to talk to you today more or less about a different field than what we were looking at since yesterday, because this is a hardcore biomedicine research community that we have. But I suppose in every research at a very higher end for a real life application, we need collaboration, just as we see in a clockwork, for example. It needs to be integrated. You need mathematicians to predict, you need biological people to, of course, give you the background, and chemistry somehow integrates as the basis of life in making molecules, in delivering molecules, and so on, and designing devices, materials. So I think the community has to integrate, and that is the key thing here, which is nice of introducing these interdisciplinary sciences in this, the concept of introducing interdisciplinary sciences was great, which is programmed within this conference event. So we are going to see briefly about what these ionic liquids are and some kind of explanations or research experience that I had personally, and also something which can be related to the biomedical field. I'm stepping slowly into the biomedical application, so I would not be probably mostly talking about direct biomedical application oriented research here, but hopefully this is going to open up a few more venues of research within your research projects, okay? So just what is ionic liquids? Just splitting into two. One is ionic. As we all understand, you need cations and anions, or positively charged ions and negatively charged ions. And the other one is liquid. We are all familiar of making liquids, indeed. One is by dissolving salts into solution, which is like the dissolution. You make a liquid. I'm not going to teach you how we make the solution, but just a visual, of course, helps a lot to understand. So, a salt in a liquid to make a solution, and the solution is a liquid. The other way is by melting. Sorry, this is not the music I want to play, but it's just to show melting by providing temperature converts the solid into the liquid state as well. But what ionic liquids are is you can make actually mixing a solid to another solid. So two salts together to earn a liquid state, right? It's just a visual, an organic salt, and it is very colorful as well, so it's clear to know. One is, of course, brown, and other is, one is the cationic counterpart, other is anionic counterpart, and even without heating, sometimes you end up at beautiful looking ionic fluids. I wouldn't call it fluids because that includes various other states, so ionic liquids. So that's what these are about, yeah? Why those end up in a liquid is, of course, because of the lattice energy. A salt, simple structure as sodium chloride, indeed has an intact structure with anions and cations packed with a definite crystal lattice energy, and it ends up to be a solid. To melt a salt like sodium chloride, we need like 800 degrees Celsius, very high temperature, to get it in a molten form. But we know that in a molten form, many things are feasible. It can dissolve several inorganic organic compounds. Well, organics almost will evaporate, as you can imagine. So it's not even possible to handle organic compounds at 800 degrees Celsius. So the power is the key here, okay? A molten lava, if you want to imagine. But if you can design something of that same power, but could be at a liquid, at room temperature, at ambient temperature condition, where we can handle it easily, that where came in the applications of ionic liquids in various fields. So the trick basically is to just designing the asymmetric structure, okay? If it is asymmetric, either in the organic, mostly in the cationic side, the lattice energy, of course, plays a key role and ends up to be a liquid here. So the special properties, what is special about it? Okay, they are liquids, they are fine, they are ambient conditioned things, and they can be handled easily. So there are some unique properties that they make them very not special, but more applicable for practical applications. One is they don't smell, they don't evaporate. There is a in realistic terms, what we explain it as a negligible vapor pressure. Everything has indeed its inherent vapor pressure, but it has almost negligible vapor pressure. They don't catch fire, they are not flammable, okay? That makes the opportunity to go and introduce this in any kind of explosive environment, right? It's just to show that an organic liquid, like any organic solvent, of course, when exposed to a torch, catches fire, whereas you see the same with an ionic liquid doesn't catch, okay? There are little videos, hopefully this presentation will be circulated and you may have this. I'm not gonna take in showing those videos to take the time. The other thing is about, as we just said, ionic, one cation, anion, but you can design them, okay? So what could be, they can be classified as designer solvents. Depending on your application, we can design from the scratch like task-specific ionic liquids. So if you want it biocompatible, you can choose biocompatible anion-cation combination in your medical application, for example. And if you need a metallic component introduced, and if it has to be a special kind of particular metallic component, that could be designed as well. So it depends on what application you need, we can design ionic liquids. And there are, of course, a lot of combinations possible. At least 1 trillion is predicted. I don't want to use this animation to take longer. At least 1 trillion is predicted because of the permutation combination of various possibilities of joining a positive ion to a negative ion, which means there is a versatile choice, yeah? The history is not anything new. It has been ever since known since 1888, taking back to the research of making ethyl ammonium nitrate, which was the first ionic liquid, but then it wasn't even recognized as the ionic liquid. It was called as a liquid salt, and it had its own application, and the first paper published by Paul Walden in 1914, that's when it started to slowly pick up the uses, but it was still not known until in late 70s and 80s when it started to explore using room temperature, when people started to explore using the term room temperature melt, yeah, not molten salt at high temperature, but room temperature melt. So the basic application or the basic research started in designing electrolytes for batteries, for applications in batteries. But ever since then, the ionic liquids, as we just went through the unique properties, are known for various fields and fundamental researches. 2 applications in real time and real life has been explored since 1990 onwards, and there are so much out there in all different fields, including the field of biomedical, which is actually taking into gathering the momentum over the last decade or so, or even less than a decade, okay? So just to recall, the molten salt, which is a liquid, like a fire liquid at 1200 degrees Celsius, the power of the liquid, yes, that can be achieved at room temperature, and that's why we are interested in this field. This, what we are going through here are all applications that somehow applies. I will come to that in a bit, how this is related. For example, as I just mentioned to you to the start, organic components, which are basically most of the drug materials are all organic components, and also biological materials are organic components. You cannot deal those things at this kind of situation. You need a milder condition to dissolve them. Indeed, there are solvents to dissolve, but the solvents are hazardous. There are so much environmental mitigation rules from the EPA and so on to use organic solvents for various matters, even for the synthesis of pharmaceutical chemistry, for fine chemical synthesis. Organic solvents are, of course, a big challenge when you prepare them in tons, yeah? For electroplating, this is how the molten salt is created to plate aluminium, for example. These aluminium, gallium, indium, which are all like high temperature molten salt, which could be deposited only at high temperature conditions, just as a molten liquid, was possible to also deposit at room temperature conditions using the ionic liquids. That takes back to the researchers in 1980s. Oster Young from America actually did all this work. And What we did in Belfast is the electrodeposition of a challenging metal, which is zirconium. It is multivalent. If you understand the term multivalent, it exists in different valencies, the zirconium. So it can have like 1 or 2 or 3 different valencies, and it becomes hard to deposit at a 0 state, which is the metallic state. And the challenge is to bring it down at room temperature to its metallic state. So we dealt with this. And where zirconium becomes important for biomedical application, for example, is zirconium. They are used in artificial bones, for example, or even making amalgams of mercury with zinc and all these dental amalgams and fillings, and there are implants. Of course, these are all has to be dealt, and these are various applications of ionic liquids where it can be deposited at mild conditions in very smooth levels as well. So we kind of have the experience, and we did the work on the zirconium and also a few other challenging metals like indium, gallium nanoparticles, indium nanoparticles, their alloys with gold, etc. has all been dealt, and it is all possible at room temperature condition for a smooth finishing. Okay, so this is not just in the research level, but it's already out there for industrial application. A company run in Leicester has this opportunity. As you can probably see, the smooth finish is the key here. Yeah. So lithium battery, this is another challenge. These days there is an aviation alert of carrying lithium batteries over the plane because it has the hazard to cause an explosion. This is mainly due to because of the electrolyte, because any battery or any energy storage device has 2 components, which is the electrode and electrolytes. Yeah? The electrolytes, either by using a non-aqueous electrolyte, which is inflammable, can cause fire, or using an aqueous electrolyte under certain pressure conditions, like for example when it is going in the sky, when it is the chamber pressure of the flight, for example, can cause a leak and also can cause a potential hazard for releasing hydrogen and can lead to explosion. These are the reasons why these are not allowed in the aeroplanes anymore. Why we say about lithium batteries to the biomedical community? Energy storage device is used in various applications, including your biomedical devices, implants sometimes, and also, for example, defibrillator, where you need a high energy discharge in one go to get the heart activated. So those kind of applications, if you want to deal it with non-hazardous electrolytes, that's where these ionic liquids could be used as electrolytes, replacing the non-aqueous or the aqueous systems. So what is special about using ionic liquids other than being non-flammable and other than being non-vaporizable? This is about having large electrochemical window. This is more specific for an electrochemist who is designing energy storage application, but it is just to show you the voltage, which is on the x-axis, is longer or larger, if you want to call it. For aqueous conditions, you will have a voltage limit of maximum 2 to 2.5 volts, whereas for ionic liquids, you can have it extended up to 7 volts, which allows you to retain more energy storage redox processes happening within this and can be used for energy storage devices. So this is something is coming up very well in the field as well, which we have some application tested in Belfast. So this is more for electronic portable devices. Having said that, this can be transformed easily into an electro implant or biosensors or related to medical device applications. And they can be made flexible because they won't leak, and the ionic liquids can be integrated into a solid state condition where it can be made flexible, right? So these are better opportunities which are all coming up in the field. And just as explained, organic solvents cause pollution, and indeed fine chemical synthesis, never mind if it is pharmaceutical synthesis, still involves a lot of organic solvent in their synthesis procedure. So there is a saying, this is not something that I innovated, but the ionic liquid community calls it, or the professor who deals with this application, Ken, he calls it as solution for pollution, which is, I think, very interesting and also straightforwardly applicable. What ionic liquids can also do is do phase separation. which is, I suppose, one of the key challenges in pharmaceutical pharmacokinetics and analysis applications, because you need to probably selectively separate some components from some streams and leave the rest. So selective separation becomes one of the applications directly applicable to your field. So as you see, the the down layer in the picture is an ionic liquid. We have aqueous layer, and we have also the organic layer. So you can have all the three layers separated, and you can selectively retain some of them in different phases depending on what application you need. So I'm not going to, just as a wee explanation, the solution here is like a metal extraction example. So a cobalt containing aqueous solution, when you contact with an ionic liquid, just mechanical shaking, agitation, or microwave reaction can phase separate, and as you see, all the cobalt from the aqueous phase has gone into the ionic liquid phase. So this straightforwardly helps to remove toxic metals from certain streams, like purification of water and so on. So that leads to the opportunity of, as I just mentioned, toxic metal removal, which could be also designed for biomedical application, I don't know. But there are opportunities which is not directly applied to human body, but to other plant conditions in this stage. So what we did in Belfast is about mercury removal. Mercury, as we all know, or probably some are not aware of this, is a neurotoxin and can cause even death, for example. But playing with mercury or using mercury and handling mercury is not it's not an imaginary thing. People do it in real life like that in gold mines and so on. So there are quite a lot of exposure for mercury to humankind, and there are also incidents caused across the world in various situations. Like this professor had to die basically because of penetrating organomercury through her gloves, and that led to central nervous system failure, and in 3 months she had to die. And there were also incidents across the world like the Minamata disease and the methyl mercury poisoning in Iraq, which are all due to organomercury poisoning. So it's not just a human related toxic metal, but also caused serious incidents in industrial application, in industrial plants. So there was a corrosion in one of the industrial spare parts called the aluminum heat exchanger, and that led to a big explosion in Algeria. So what we dealt in Belfast, which I'm working for like past 7 or 8 years with the petrochemical industry. As you see, there is a very vast, versatile range of application, as you can see, from pharmaceutical to petrochemical, from crude to fine chemical. Elemental mercury removal from natural gas is something what we dealt. Why I show this here is because how is this possible to transform a little laboratory scale research into a 60-ton units? Luckily, fortunately, I had this nice experience to visualize this whole transformation. So we designed an ionic liquid which can contact with the elemental mercury. In this case, it was a copper-based system which can do the redox reaction. One can reduce, other can oxidize, and elemental mercury is transformed into oxidized and captured into the ionic liquid system, and that's how removed. But basically, this concept can be applied to any other metal extraction processes, yes? In this case, as you just see, the 30 milligram ionic liquid containing solid support. Okay, in this case, in a real plant for 60-ton level, we couldn't fill the whole 60 tank with fluid ionic liquid. Also, the gas to liquid contact is not possible, and this shows that we can also put them on solid support. So basically, it's a silica supported ionic liquid material, and then scaled up to a pilot scale, and then transformed into a 60-ton unit. So this is not only one of the ionic liquid processes, and this was not going to be the last one as well. This is the Eastman company had the first ionic liquid process, excuse me, established in 2007. So basically it was used as a catalyst in the oligomerization process, yeah? And this is one more process. These are not directly related to pharmaceutical, not directly related to biomedical application, but I'm sure this is related to pharmaceutical industry. For synthesis reason, ionic liquids could be used as catalysts and could be easily removed and separated because they have their unique separation properties as well. So there are different processes. This is a very schematic representation to use ionic liquid as a catalyst and could be removed just by phase separation. And this takes back to the Nobel laureate using this ionic liquid in his next step of advancement in this process. So biomass dissolution is something which is coming up. The bio-waste is a big challenge to be dealt, and can that be converted into useful products by using ionic liquid strategies? Yes, there was a paper which came up in 2002. Basically, you can dissolve cellulose or cellulose carbohydrate, natural carbohydrates and sugars into ionic liquids, and you can transform them into an amorphous form and then can take sheets out of it and so on. Recently, there has been a big process commercialized, and that's called ion cell process, which basically makes cotton fibers regenerated from bio-waste. So this is possible. Carbon capture, okay, if you can't really remove all the biomass out of ionic liquid, and if you have to capture them from the emissions that comes out as carbon, that could be achievable as well. So liquid magnets, another application. I am not going to stay longer. So basically, ionic liquids can be even carried to the moon. It's just because they don't have they have negligible vapor pressure, in the sense they can retain at minus temperatures up to minus 200 sometimes, and also that they don't evaporate and not flammable. They can be carried to the moon. So in this case, what we are seeing is a lunar telescope deposited with a mirror, silver mirror, which could be used in the moon. And that was a research with NASA. I am not involved in that, but just to show you all the wonderful opportunities. So stepping into the biomedical application, we have recently started to explore about using these ionic liquids for biomedical device materials synthesis and process. Before going into that, I don't have to show you probably what is the challenge in drug industry about polymorphism. Basically, polymorphism is about existing of the same drug in different morphological condition change due to temperature or due to time conditions, that it changes one form to the other, sometimes could be also ending up to be a fatal in the other form. But if there is a possibility to design those drugs, which are basically solid salts, in a liquid form, then you rule out the polymorphism challenge from this process. So there has been a few researches already going on, and there are some basic pharmaceutical components designed to be liquids, and they have been demonstrated that they are not going through the polymorphism and other structural changes, but it's a long way to go. As we just saw the timeline of establishing a pharmaceutical chemical to a human application, except for in the reasons of Ebola or anything, it's going to be a long time. But also for hospital-bound infections such as MRSA, ionic liquids have proven to be much more effective and also retain the antimicrobial activity for a longer duration in general, but of course not commercialized yet, since there are of course things to go through. What I am particularly interested in the recent years is to design a medical implant, or just as an example, a urinary catheter which stays in the body, and because of staying in the body for a long term, that it develops biofilm and then leads to secondary infections, and therefore will be nice to have a catheter which can release the drug only when it spots the biofilm formation, controlled release, whereas not diffusing. Of course, there are catheters available with drug incorporated or drug coated catheters, but which also diffuse spontaneously the drugs when it is not even needed. But if we can control the release of drug from the catheter or the medical implants only when it is needed using some electric potential. So this is kind of interest that I am looking at the moment. And as you can imagine, the challenge is to design such a polymer or a material which can be electroactive as well as biocompatible. So this is just the state of art. As I just said, there are, out there already some technology definitely, which are all about disposable catheters using silver coating and antimicrobial or antibacterial coated catheters and so on. But the challenge is to get something which is more active for a longer duration for old age patients, for example, to avoid multiple invasion and so on. So this is just my approach, which could be just minimum consumption at the right time using a mild potential. Indeed, thinking about potential urinary catheter, don't get horrified that you will be electrified, but it is very mild pico or the micro amperes of current which we won't even feel. I'm sure we have electrical experiences in the body when we go through different other medical devices anyway. So conducting polymers, not just the ionic liquids, but in here we need the I am at least interested with the use of conducting polymers, which are redox polymers that can take an ion or take an anion, in other words, when it is doped, what we call, and then when released with a different potential, can release the same anion in the form of a drug, which is in the acid form in the biofluid. So they can be doped and de-doped using electrochemical potential. So the challenge, or at least the story, is about making a conducting polymer and biopolymer composite, triggering them with the electrode potential and loading them with the drug, and then at the target site with a different potential, just release the drug. So this is not something new. This has already been established with the conducting polymer scenario, but the challenge is to design them to be more flexible, because conducting polymers are naturally ending up as powders and brittle and cannot be devised into flexible conditions. So the challenge was to use ionic liquid strategy and then explore the flexibility of transforming these redox or speaking polymers, electroactive polymers, into a flexible form, which has been successful to some extent at this stage. And if I can show you, the flexibility is quite all right. Instead of a powder, at least it's a film, and it's has its polymer properties retained to be flexible. Operational under most of the real life world application, it's stable up to 200 degrees Celsius. This is a TGA, which is the thermal decomposition study. As you can see, the polymer composite, which is the C, which also incorporates with the ionic liquid, has been stable up to at least 200 degrees Celsius. The red curve is that what I'm talking about here. And when there are already technologies which can graft the conducting polymer on flexible things like paper, but what happens is, even just by using a sticky tape test, you can remove, or the films can be, poorly adherent to the substrate and can be removed. But in case of processing using the ionic liquid technology, which unfortunately I'm not able to describe in detail because of patent and other conditions, but in the sticky tape, which is on the right hand side in this direction, doesn't show that it is poorly adherent, but it is all in one form. And this is just a brief study. It's a lot of technical information here. I don't want to bore you, but what basically I'm saying is, when we trigger the figure on the left hand side in this direction is a cyclic voltammogram. So basically it's a redox active polymer, so that has been achieved. And this is the UV spectrum with the chronoamphometry with the inset. What basically it's showing that when we have the potential applied for release of drug for certain for the certain duration, you see the UV spectra changing, indeed reflecting the concentration of the drug released into the body fluid. So it's a very basic preliminary study which has been demonstrated so far. All what I am trying to show you here is the power of a lava is still there in ionic liquids, but they are mild and they can be handled very easily under ambient conditions. This is something I'd like to really highlight, and I like this. There is always a challenge when you go towards a new direction, but I suppose there is a thrill and you get more satisfaction when you get the problem solved. And I must thank a lot of people around, and even you, for having me here and listening to me patiently. Indeed, the rest of the team back in Belfast, as well as the international team, and for the L'Oreal Fellowship, which has been recognized me, and to the Royal Society. Thank you. Five minutes for questions. Anything pressing at this stage, or I'm always happy to answer when we have discussions outside.
Very nice talk, Geetha.
Thank you.
I have a question regarding the urinary catheter use, ionic liquids. Correct me if I'm wrong. What I understood is you're going to deliver antimicrobials when it's needed using those systems, right?
It's not very audible, yeah.
Okay. You are going to use the ionic liquid technology to release antimicrobials when it is needed.
Yeah.
So how do you determine the timing, the correct timing, when to release it?
That's a very good question, because these polymers, or at least in future, this has not been demonstrated yet, but it is expected to be feasible. They are biosensors, active to electroactive response. So if you have like a film formation, or even like the sensitivity of the electrochemical techniques are very low, yeah? I mean very high, sorry, the sensitivity is high, the detection limits are very low. You can even see the response of pico levels of adherence of microbacteria or biofilm on the polymers. So if you can monitor in real time from the current changes that there are biofilm formation, and you can also quantify from the technology, from the technique, that how much is the drug needed. This is all back calculation. It needs a lot of research done, but it is feasible. You can sense it as well as quantify how much of drug needed, and then you release the potential for that particular period to release the certain amount of drug. So it's controlled electrochemically, if I want to say that way. It's a dream, but it's feasible.